So, hello everyone. So we have a question about the importance of kinematic viscosity, and the question says that we have four tubes with the same volume, and they are falling under the effect of the gravity. The question says, release them according to the increase of the falling speed. Which one falls fastest and which one falls in the slowest rate? So if you see that we have the ideal fluid with no viscosity but with some density, so we have the glycerin with some viscosity, and there is the density about the same size of the water, and the water has the same, almost the same. So this one is 68, this one is 34 viscosity as the mercury. So they have the different temperatures. So the question says which one will fall the fastest. And so if we analyze them, we will look at firstly the speed, and then we will talk about the importance of kinematic viscosity. So here we have two opposing forces, let's say. So one is that the fluid falls under the effect of the gravity, which is determined by m into rho g. So m is rho into volume into g. Since each of them has the same volume, it means that the speed is determined by the value of the density. If which one has the highest density? Mercury. So it means that mercury may fall with this highest speed, and then the glycerin, and then water, and this ideal fluid, one of them. Okay, we don't know exactly. If you look at the density, this is the first case. Now, while the fluids fall, we have an opposing force, which is the viscosity. Okay, this viscosity opposes the motion in downwards direction. Therefore, then we should see the value of the viscosity for the speed. So ideal fluid doesn't have any viscosity. It means that it will fall with the highest speed. It's possible, we don't know. And the glycerin, it has the viscosity which is the highest among all of them. Okay, and then water and the mercury. So it means that when it falls under the effect of the gravity, viscosity opposes it. Okay, therefore here the value of viscosity alone is not important, value of the density alone is not important, the ratio of them is important, mu by rho. Let me write it, mu by rho. Highest means the slowest rate, slowest speed. Okay. In our case, mu by rho for the ideal fluid is 0. It means that it is fastest. Okay, mu by rho for glycerin is the maximum among them, therefore this one is the slowest. If you compare mu by rho of the mercury with water, mercury has high density and water has the low density, but we should look for the ratio of the mu by rho for mercury and for water. So if you calculate it, I've calculated the values here, so you can see the value. So if you calculate the values for 4 degrees Celsius, mu by rho for water is this amount, for mercury is this amount. It is smaller than water. It means that mercury will fall faster than water. This one is faster than water. And this one is, if you list it, you will have the fastest as A, and then you will have slowest as B, and then you will have the water, and then you will have the mercury. So there is a small video, so here it shows the falling of the mercury under the effect of the gravity. It is very difficult to say it is mercury or water. Okay, so you see that this one is, let me show it one more time. Yes, and now let's see the different meaning of viscosity, kinematic viscosity, which is mu by rho. This one is kinematic viscosity. Okay. We will compare two fluids. One is ideal fluid and the other one is the glycerin. Okay, for ideal fluid you have the same velocity everywhere. This has the same velocity because here you don't have any no slip boundary condition. Okay, so you don't have no slip boundary condition. Okay. Therefore the velocity is the same everywhere. Okay, write it. At each cross-section of the pipe, you have the same velocity, and because mu is 0. So what happens is that the fluid velocity momentum, so this one is mv of the fluid, is distributed uniformly in downwards direction. Okay, here fluid viscosity momentum mv is distributed uniformly in downwards direction. Okay, mv is, so we can write mv as rho into volume into v, velocity. Since this fluid and the other fluid has the same volume, and therefore their momentum in downwards direction is only determined by the value of the rho, okay, and as well as the value of the v. And this part is the same for both of them. Okay, now let's look at glycerin. So how the momentum is present here. So here for the glycerin, you have the zero velocity at the H. Okay, here you have the zero velocity, and here you have the zero velocity. Due to no slip boundary condition, you have the zero velocity. This zero velocity or zero momentum, let's say 0v, is same as 0mv, zero momentum. This zero momentum affects the momentum of the next layer of the fluid, and therefore its velocity decreases. Another fluid layer, you have another fluid layer, so you will have a shape, parabolic shape, for the decrease of the fluid velocity. And the profile will be something like this one. Okay, so if you compare these two fluids, which is ideal and the glycerin, so you will see that the momentum of the ideal fluid in downwards direction is redistributed. Okay, so let me write the concept. So mv of glycerin, okay, is redistributed due to presence of viscosity. So this viscosity redistributes the momentum of the glycerin, and this redistribution of the momentum decreases the momentum of the glycerin in downwards direction. Therefore, decreases. Okay, mv in downwards direction. Okay, it decreases mv, and we have said that downwards direction mv is determined by rho, volume, and velocity. Okay, and this is viscous losses because viscosity is non-conservative force. Therefore, it decreases the momentum of the fluid in downwards direction. So mu by rho. So what happens is that the fluid tries to maintain its momentum. So fluid, okay, tries to maintain its momentum in downwards direction. Okay, but what mu is doing, it redistributes the momentum and it decreases mv in downwards direction. Therefore, you are comparing, we can say, two forces. Okay, one force is trying to diffuse the momentum and to decrease the value of it, and redistributes it in y direction, and then the other one, this one is the y direction, and then the other one tries to keep its momentum next direction. Okay, it tries to maintain its momentum in downwards direction. Okay, this is the definition of the kinematic viscosity.